Good afternoon, everybody. I hope you guys are doing well. It is 3 p.m. in the afternoon, a few minutes past, and my cat has decided now is the time to scratch. Wow, he darted out of the room faster than I've ever seen him move before. That was nuts. He'll probably be back. But anyways, so today we are doing function templates. Now, this lesson, what we're looking at is an hour and 20 minutes or so with some change of actual lesson, and I think today and Monday are like the last days that we'll probably be able to do like where we can consistently do one chapter a day. Today is probably going to be like the second to last day of that, because after that, once we get into classes is like a 2.5 hour lecture. Hey! 1 second. I'm going to have to deal with my cats real quick. Alright, sorry about that. One of them is now in gay baby jail, separated from the other. Alright, so as I was saying, so we have our... Yeah, so today is like the second to last day that we'll be able to do like a full chapter in a day. So we'll be doing chapter... Today, the goal today is to complete chapter 15. Try to understand function templates. That's the plan for today. And then after that, chapter 16 is probably the last one that we'll be able to do one in a full day. After that, it gets a little bit long. But on the upside, what this means is chapter 15 and 16 are like full days. Then and we're after we complete chapter 16, there are only 3 chapters remaining. They're very long chapters, and there's going to be a lot of learning that we're going to have to do in not short time, but in before we understand. What am I trying to say? I'm trying to brain more gooder. There'll be only 3 chapters before we've completed this. There'll be long chapters that we hopefully understand properly. You know, hopefully it doesn't get too difficult to do. And then I think around after I complete this, what I'm gonna see if there's like a any one of those certifications that you can that I could maybe take to try and to see like, okay, how much did I learn, right? How effective was this? So we'll probably be looking at that in a couple of weeks. But anyways, I'm gonna stop rambling now. We have a lesson to learn. Function templates. Let's get over like here. Boom! Look at that. No scuff whatsoever. All right, take it away, Mr. Yakwaya.
This new chapter, where we're going to be learning about function templates. Function templates are a mechanism we have in C++ to set up blueprints for functions and have one point of control to set up the function, but the compiler is going to generate the actual function that gets called when it sees the function call. So this is going to solve the problem we had before with function overloads. If you look at the code here, we have multiple overloads for the maximum function. But what we really are doing in the body of these functions is the same. And suppose you have 12 or 13 or 20 overloads of the same function, you're going to be basically repeating the same logic in the bodies of this function. And this code repetition is bad. Function templates are an effort to solve problems like this. The way they work, you set up a blueprint for your function. And this is the syntax to do something like that. You say template type name T here. Don't worry about this syntax. We're going to have a chance to go through it in detail.
Thank you.
But if you do things like this is going to be a blueprint for your maximum function. And the compiler is going to use this blueprint to generate an actual function when you call this function. And this is going to make things super easy. I realize some of this is really cryptic, so let's head over to the next lecture and let you set up your very first function template.
All right, let's do it.
Go ahead and finish up here and meet me there. In this lecture, we're going to set up our very first function template. And again, function templates are a mechanism we have in C++ to avoid code repetition. For example, if you are setting up function overloads. If you look here, we have our max function, and we have multiple overloads for this function. We can call it with int, double, and string view here. But if you look inside, you see that we really are repeating the same logic. And it is even possible to have dozens of overloads if you want to support tons of types for your function. And this code repetition is really bad. Function templates are a mechanism we have in place to avoid things like this. And what you do, you set up a function blueprint using the syntax you see here, and your function template is going to be prefixed with this template type name T thing here. Type name T is going to be in these angle brackets. And then you're going to put the blueprint for your function. T is a placeholder for the types that you use in your function. You see that T is in the return type here. It's in the parameters that we pass to the function. And because it is the same character here, all these things have to be of the same type. The return type, the first parameter, the second parameter, they have to be of the same type.
So if you want integers,
they're all function template set up like this, you're going to implement it like we see down below here. It is nothing complicated. We just set up the prototype for the function on top. And inside, we put our implementation. You see here, we have separated this into function declaration and function definition. But inside, you see that it is the same logic we had to compute our maximum between these two parameters that we pass to this function. So how does this work? When the compiler sees you call this max function, for example, as we are doing here, it's going to look at the types that you pass in. And in this case, A and B are of int type. So it is going to replace the t in here for int, and it is going to generate a function in your code. And this really brings up a big point about function templates. Many people think that function templates are actual C++ code. They're not. They're just a blueprint from which the compiler is going to generate the actual function that is called by the compiler, for example, when you issue a call like this. Again, function templates are not real C++ code. They are just a blueprint that the compiler uses to generate your function based on the arguments you pass to the function when you call it. So when we issue the call like we do here, an int version of our maximum function is going to be created. So the compiler is basically going to go in and replace int for t here. The return type is going to be int. The first parameter is going to be int. The second parameter is going to be int. It's going to go in the definition. It's going to do that. And we're going to have an int function. If we issue a call with c and d like we do here in the second line here, then the compiler is going to see that c and d are of double type. So it is going to generate another function from this blueprint.
See, okay, so my understanding of this so far is that it makes sense. It makes sense what he's doing here with like the compiler generates a function that uses A and B, and then it's like, oh, those are both integers. Does this mean that it's just not possible if you mix types? Like if I do A and C, for example, is it going to generate a double by virtue of the fact that it's a double? Or because like a double takes more memory, or is it going to just be like, hey, compiler error, this doesn't work? That's kind of my question with it, and it seems I'd guess that it just doesn't work because you have to have the same. It looks like you have to have the same thing 3 different times. But I mean, let's keep going.
Right here, and it is going to replace in double. Then we're going to have another double function. If we go to the third line here, we're going to do the same. We're going to call it with strings, and it is going to generate a string version of the maximum function here. So what we achieve with function templates is to avoid several overloads for the same function, and we have one point of control in our code. But the compiler is still going to generate these function overloads. But one thing about this is that if a function is not used, for example, if you never call our maximum function with string, then the string version is never going to be created. The compiler is going to generate the overloads that you only call in your C++ program. And this is really all function templates are all about. They give you a mechanism to set up a blueprint for your function, and then the compiler is going to generate actual functions based on what you call in your C++ code. Okay, we have said this, but I want to emphasize this again. Function templates are just blueprints. They are not real C++ code. And when we hit Visual Studio Code in a minute, we're going to see a tool that allows us to see how the compiler instantiates your function templates based on the arguments you call your function with. But keep this in mind, function templates are not real C++ code. The real C++ functions get generated by the compiler when you call your function. And another thing I wanted to point out is that once a function template instance is generated, for example, the int version of our maximum function template, then if it is needed again, the compiler is not going to generate that again. It's going to see if there is one generated already, and it is going to reuse that. Okay, this is really all I have to share about function templates at this point in this chapter. For now, we're going to head over to Visual Studio Code and play with this a little more. Okay, here we are in our working directory. The current project is trying out function templates. We're going to grab our template project. And one thing I should point out here is that our template project has been now updated to have the launch.json file, which is going to allow us to debug our programs. So you should use a template That includes the launch.json file
Um,
here. That's going to allow us to debug your programs, and we're going to do that in a minute when we have set up the example here. So we're going to grab our template files
wait,
and
are
put
you not
them
going to
in
show me how to
place.
set up
And we're going to open
launch.json?
this little guy in Visual Studio Code by dragging and dropping on top here. This is going to do our job. Then we're going to open up the main CPP file, and I think we should close the left pane here. We don't need it anymore. And we're going to clean this up a little bit. So one thing I want to do is to first do things the bad way. So we're going to set up a max function. Let's call this maximum. And it's going to take int parameters. And we're going to return the maximum between A and B. And the way we do that, we say A greater than B. We are going to use our ternary operator here. We're going to put a question mark. We're going to return A or B. And this is going to be our function. But suppose we need another function that works on doubles. If we put double arguments in here, the compiler is going to insert implicit conversions from double to int. This may seem to work, but suppose you use a parameter type that is not convertible to int. For example, you use a string or something. Let's put in std string here, just for an example. So we're going to say maximum std string A and std string B. And we should make these const references because we're not interested in modifying these strings here. Let's finish the name here. And we're going to say const std string reference A. This is much better. It's going to avoid unnecessary copies of strings. And we're going to say const std string reference B here. Then inside, we're not going to do anything different. We're just going to use the same logic. Okay, let's do that. Suppose you have another function which takes, what should I say, long int. If we need that, we need to copy this function and put that in. Okay, we need to do that, and we're going to change this to long int, and we're going to do the same here, long int, our parameter, and we're going to say the same here. And you see, we are setting up a lot of functions with basically the same thing inside, and this is a lot of code copies. Suppose we have this function maybe 20 times. It is possible, or even worse, the logic in this function is really long, maybe 20 or 30 lines, and we will have to repeat this thing in our code. So
you can use using namespace std just under your include statement, so you don't need to explicitly specify std something, and can just write something instead, by the way. Oh. What? So, was it? I just type it like this? Using name? No. It would be include, maybe? Using namespace std. Yeah, no. I have no. This is like the. I just using namespace std. Is that? Okay. I've generally been trying to just follow exactly along with what's being done because I have never done any of this before. So like so I'm kind of a little bit, I'm probably as much of a beginner as you could be when it comes to anything coding. You can just write string now, just use whatever works for you. Okay. But basically what you're saying is that it gets rid of all these STDs. I can just do string maximum. All right. That's good to know for the future, at least. I think I think I'm just gonna make my shit look like his shit, because that's generally been the the vibe I've been going with. But it's good to know that. for sure. Because it's very STD. It's very heavy because he uses STD string a lot, and STD standard and STD or STD standard like NDL and all that good stuff. It is interesting though. Why are there so many different ways to do the same things? So many different, or not even the same thing, but like it's like different libraries and stuff. And then that was it. Using namespace std. What even would that be considered? This isn't a library. What is this? What is this? If it just works like that. Because like this is like, okay, we're including essentially another thing of code. But what is it called when you do this? Writing namespaces explicitly is better when you have a lot of namespaces in the same file, but most of the time you'll just be using the std standard library. Interesting. What the hell? Oh. But yeah. Oh boy. Oh. Oh. All right. I mean, wouldn't be the first time that he's. God, dude, I just got fucking like I totally got I just got like stun locked by my own brain. All right, what's it called?
The designers of the C++ language saw this problem, and they
IOStream is a header
say, why
file.
don't we set up...
It's a C++ file that contains code for stuff like cout string that we import to just use, but there are a lot of header files you'll see later. We did use he showed us how to use like certain what was it? We used like include, and then it was fucking we had created our own header file essentially to use at one point. It was like we like named it whatever it was, file.c or whatever or something like that. And like that was like for a separate lesson. That was very that was a that was when we were talking about like declaring and using functions, and it's like we had one header file that just declared a bunch of functions, and then one that like gave the definitions for each function, and then all we did was call them in the main file. That was a pretty interesting lesson, I think.
A one point of control where we can set up our logic to do the maximum, and we let the compiler generate actual functions based on the arguments we call our function with. And they came up with function templates, and that's what we're going to see. So we're going to take out all the other functions, and we're going to turn this maximum int function into a function template. The syntax to do that is ridiculously easy. So we're going to say template. This is what you say. You put an angle bracket, and you say type name, and you specify the placeholder for the type in these angle brackets here. This is the syntax you have to use. Then you have to specify your function in terms of this placeholder t. It is going to take the place of the type. So for example, here we want to return int. We're going to change this to t, and the parameters are going to be taken by value t and t. Let's do that. And now we have a legal C++ function template. It is going to take this template here and use it to generate actual C++ functions. So for example, if we go in the main function here and say int result equals maximum we should say, and say x and y, for example, let's create these variables on top here. So we're going to say int x, and we're going to put in a 5, and we're going to create a y and put in a 7. Why not? Now this function is going to store the result and print it out. Let's do that so that we can see that this actually works. So we're going to say result and say result. this is going to do. And if we build and run this program, we're going to use GCC. You're going to see that the build is going to be good. And build finished successfully. We can run this program like we always do. Let's bring up a terminal and clear a little bit and run rooster. You're going to see that we're going to see that result now is 7 because that's the maximum. You see, it is working here. So
well, it works.
Is this make?
That's so. It's the fact that this can so I assume that this works with any two or any of these, any type data type. Jesus. Ugh.
Mechanism working here. The
Please
compiler
explain
is
it.
basically looking
How does
in
this
the
work?
main function here, and it is noticing the call, and it is going to look around and see if it can find a declaration for the maximum function here. It's not going to find it because there is none. Then it's going to look at the function templates it has in here, and it's going to see that it can do a replacement and replacing the types that we are passing in here. So it is going to do that. It is going to take this template and it is going to replace t by int. And then it is going to generate a function that basically looks like what we have here. We're going to copy this and we're going to put this in. The compiler is going to take the first t here. It's going to turn that into an int. It's going to take the second one here. It's going to turn that into an int. It's going to take the third one.
So it just takes all of them and turns them into ints.
Turn that into an int. And we're going to have a function definition for the call here. This is what the compiler is
So
going to do.
Does it work if I mix types? That's the big question. Some of you might be
thinking, is there a way to really prove this? And somebody was nice enough to design a tool to let us see this function or template instances generated by the compiler. And I happen to have that opened. It is a web-based tool, so you can use this in your browser. Just go to cppinsights.io. And then we're going to grab the code we had in our main CPP file. We're going to copy it all. And we're going to go back to our browser and remove whatever I had in here because I don't want.
All right, let me see. cppinsights.io.
This anymore. And I'm going to put in my function template. If we want, we can even take this stdc out statement because we don't want all the junk that comes with it. We are just interested in looking at the template instances generated by the compiler.
You have to make 2 templates if you want to mix file. T, the template, only signifies one type. Ah. Okay. So like if I make a second what is it? 2 templates if you want to make. So if I just make a second template, would I be able to do then like an int and would it be able to take the maximum between an int and a double? Right, let's copy this in here. He commented out this and he commented out what was the other thing he commented out? The STD one.
Now that we have the code in here, we're going to see what the compiler generates because of the call we have here. I think I could increase the size of the font here so that you guys can see this. I think this is a little better. Then if you hit this play button here, let's click on it. It's going to do its processing, and then the code generated by the compiler is going to show up to the right here. You see, it has detected that we have called the function template on line 13 here. You see this line is highlighted. And then if you go to the right, we're going to see the functions generated by the compiler. So if you go here, you see that we have an int version of our function template. And another thing I should...
So then it generates this. So we created this and then we called this template type name T, type name N. Use T to signify one type, N to signify any other type. Oh, okay. That's actually really interesting. I assumed, I guess I kind of assumed that this was like that T was used for kind of everything in the case of templates because T is, template, whatever. I didn't, I, I guess I just didn't put together that you could use another one. So then this thing, first instantiated from insights CPP 13. Then it uses if def insights use template, and then it generates this. So it looks like it generates all of this based on the fact that we have a template and this, and then call this. That's interesting. That it just creates code wholesale by the looks of it. Wow.
Proof here is that template instances that are not needed are not going to be generated by the compiler. Another way to say this, the compiler is only going to generate the template instances it needs. And again, a template instance
Yeah, the compiler is
is
pretty smart.
what
No
you have
kidding.
here. The
It's
function,
incredibly
the
smart.
actual function that is callable by the compiler generated from your blueprint. So if, for example, we change the type of our parameters to double, let's do that. Okay, so we changed our types to double.
So if we change these to double, I was not expecting to be using a web tool today, but I'm not going to complain.
We're going to hit the play button again. You're going to see that now it is going to generate a double function here. You see that here. If we change this, for example, to what can we use? Let's use long int. Like we did in our lecture, we can do that. We can say long int. And if we hit the play button, that's what is going to be generated by the compiler.
Wow.
So hopefully this...
It just puts all that information in, huh? Double, long int, long int, boom. Oh, sorry about that. I had to sneeze. Oh boy. But it just kind of does any of these, huh? It's kind of insane to me that it can just do this. I mean, I guess what it's generating is this, but still. It can just kind of grab whatever.
Proves that the compiler is only going to generate the instances that are needed for the calls you do in your C++ program. And this is really function templates are all about. Okay, now that you know this, let's set up a few more examples to see that this really works. So let's change the types of these guys to double. Let's do that. And we're going to play with this a little more in Visual Studio Code. And let's use double literals 5.5 and 7 or 78.7 here. Let's do that, 78.7. And we're going to build this. And one thing I should point out is that template instances are generated when the compiler is doing its job. And then they are going to be put in the binary representation of your source code. So the build is good. As you see here, we can clear and run a rooster. We're going to see that the result is 78, and it is transformed to int because we are assigning to int here to really get the correct.
Yeah, this is just this is an integer, so it's cutting off the decimals. To be fair, the actual GNU compiler generates a machine code rather than C++ code, but still very cool. I mean, yeah, the machine code being like the actual binary executable. It's pretty interesting. I'm impressed with how much you can do, but I guess I guess the amount of things that you can do with code is kind of, I mean, not I don't know about literally limitless, but pretty much functionally limitless.
results here, we should use auto type deduction. If we do that, the compiler is going to deduce the type of result here based on the return type of this function, or the function template instance, I should say. Now we're going to change this to auto to do auto type deduction.
Auto.
And if we build again, we should see a double printed out correctly. The build is good, we can clear and run rooster. Now we have the correct value printed out from our function template here. Let's change this to std string. We can do that. So let's include the string library, and we're going to change these two guys to std string. Why not? Std string. X is going to be a string literal. Let's use hello, for example, and for y, we're going to say std string, and we're going to put in a world here. Okay, this is going to do. And you notice that we don't even have a compiler error. Visual Studio Code is not complaining. The compiler is going to look at the types we call our function with, then it is going to generate an std string version of this function. And what it is going to do, it's going to replace in t and replace that for std string. We can actually put this thing entirely in CPP Insights. Let's copy this code before we run it so that you can really see what is happening here. We're going to take out whatever we had before. We're going to put in our code, and then we're going to hit the play button here. It's going to generate our thing. We wait for it to do its thing, and if you look here, you see that it has generated std string. This is really a compiler representation of std string. We don't have enough.
Hold on, let's take a look. First instantiated. Okay. std basic string character, basic maximum, and it returns. Yeah, it turns these into basic string characters, and then returns std operator a plus b. Oh god, we use it creates a ternary operator here. That's so cool. Why is it so smart? What is all of this though? What is all of this? I'm sitting here with existential dread. I haven't even been fed yet. Oh no. How you doing, Doc? Alright. I exist outside the quandaries of morality. Uh-oh.
Tools to really understand this, but hopefully you can see that it has replaced t with some other type we don't know yet. std basic string car. It has a few things inside that we don't really know yet. We will have to learn a few more things about this as we progress.
Yeah, we're gonna have to learn a lot more.
For now, I want to prove to you that the compiler is doing the replacement. You see, t was replaced by this thing here, std basic string, and we have angle brackets, and this entire thing is really std string in the eyes of the compiler. Okay, now that we know this, let's go back to Visual Studio Code and run this. We're going to build with GCC, as we always do. The build is good, we can clear and run rooster. We're going to see that the maximum is world, and this is going to be using the greater than operator, and this is going to compare two strings based on this. And we know that W here comes after H in lexicographical order. So the comparison that is done here is lexicographical for these strings here. Or I should say, it is comparing things in alphabetical order, in A, B, C, D, E, and things like that. Okay,
well,
now
it's A, B, C, D, E, and like I think, if I'm not mistaken, lowercase letters are all after uppercase letters. So they're all, if I'm not mistaken, all lowercase letters are greater than all uppercase letters, and then all numbers are, I think the numbers are the least. I think that they're the ones that come first in lexicographical notation. I don't even know if that's the right word for it. And I'm now just looking at the clock, wondering why it doesn't stop. Because time marches ever onward, brother.
Have a big idea about function templates. They are just blueprints you use to generate actual functions, and this is going to allow you to avoid multiple function overloads as we have seen before. One thing I want you to see is that you have to be sure that the logic you do inside your function is supported by the types that you pass to the function. And I'm going to show you what I mean here. We're going to set up another function template. We're going to say template type name t. We're going to set up another one, name, and we're going to use t here. You can use this however many times you want, and then we're going to set up a function which is going to do a multiplication. So we're going to say t, that's going to be the return value, and we're going to say multiply, and we're going to multiply two parameters. We're going to say ta and tb, okay, and we're going to put in the logic, and we're going to just return a multiplied by b. This is our multiplication operator in C++, and we can use this function. So for example, we can comment this out, and we can set up two variables. We're going to say int x, and we're going to put in whatever we had before. Let's put in 5, and int y, we're going to say 7. I think this is what we used before. You can really put in whatever you want. And now we're going to call the multiply function template. So what this is going to do is to generate a function template instance, which is going to be of type int. It's going to do a replacement in here and replace t with int. And then we're going to multiply two int parameters that are passed to this function, and we're going to return int.
Yes, it's the ASCII order. You can know a character's ASCII by doing int n equals a, and then printing n using cout. Yeah, I think we did that way back when we started doing that. Select the lines and control slash to comment out multiple lines. I knew there was that was that was told to me before, but I fucking forgot what it was. I think I was trying to do like shift, and that just gets rid of it. I was like, that's weird, and then I tried alt, and that doesn't do anything. Okay.
And if we do that, we're going to get 35 printed out. Let's prove this. We're going to use GCC to build. The build is good. We can clear and run rooster. We get a 35. If we change this to double, it is going to work. So let's change this to double and maybe put in 5.1 and 7.0. Why not? And then we're going to see what we get. We're going to build with GCC. The build is good. We can clear, run rooster. We get 35.7. This is what we expect. But watch what happens if we try to use the std string types. Okay, I want you to see that. So we're going to enable our std string variables here. And if we try to build, we're going to get a compiler error, but I want you to try and guess why. Why do we?
All right, let's see. Hold on. std string y. I'll do this one as world. Try to make my stuff look like his stuff. So we have like this. Actually gonna move this like so. Okay. So we got hello and world. And now we're trying to multiply them together. And we get a compiler error. I assume it's because it's strings, and multiplying strings doesn't really make sense. Let me see. Terminal, run task. So we gotta go. So it says multiply with this. Alright, so color always an instantiation of t multiply t required from here, line 24, multiply x and y. Error, no match for operator. Operand types are basic string character and basic string character. So it's because multiplying strings doesn't really make sense together. You can add them, and then it kind of pushes them together. No match for operator for std string, as in the operator star is not defined for a string. Yeah, this doesn't mean anything. Multiplying these two together, like it doesn't make sense. It's like multiplying it's like asking for the square root of onion. It doesn't really make any sense to do that. Even though the answer is shallots, it doesn't really make any sense to ask for the square root of onion. So I think if you add these, I think if we had created one of these for addition, all it would do is push them together into like one sentence essentially. But for the purpose of multiplication, for this symbol doesn't mean anything. We'd have to find a way to make this mean something to the compiler, I guess.
We have this compiler error. If we look at what GCC is saying here, it is saying in instantiation of our function template required from here and no match for operator multiplication here. And this is the problem. The compiler is going to do what it knows to do. It is going to do a replacement in our function template, and it is going to replace t by std string because that's the type we are using as an argument here.
You should keep in mind that it's purely from programming POV rather than logic. If you want, you can manually define the star operation on string to do anything you want, and then it'll work. I mean, yeah, that makes sense to do it. But like, because it doesn't like, it's essentially like almost like an undefined thing, right? Like this doesn't mean anything in the context of string operations, right? It's kind of the way I'm understanding what's going on here. Like this, if we changed this to be the same as addition, like if we changed its meaning, then then it would probably work. To like, I don't know, if we just made it the same thing as a plus, or made it operate the same way as a plus, or any other number of things that we could do. It still doesn't really. I feel like I would imagine that all of the stuff that you can do with strings has already been defined in some useful manner. Yeah, though ignore this for now. That's a topic later called operator overloading. Oh boy. Operator overloading. That sounds function overloading was already kind of like, wow, that was confusing. Why did we do that? I mean, it made sense to the reasons that that were explained, but it wasn't like, it seemed like one of those things that I was kind of curious as to why you would want to do it.
The problem is we can't really multiply two strings. If you try to multiply two strings like we do here, it's not going to make sense. What do you expect to get if you multiply two strings? It doesn't make sense. The compiler doesn't know what to do with this operation. It's going to give you a compiler error. Okay, to really drive this home, let's go back to CPP Insights and put in the code here and see what is generated by the compiler. You should use these tools to your advantage because they really help in understanding what is going on. So let's hit the play button here. I just put in my code and it is going to say compilation failed because we have the same error. CPP Insights needs to compile the code correctly to give you the template instantiations. But here you see that it is basically giving us the same error. Let's try and see the entire thing here and see if we see the real error, and we can't really scroll around with this. I'm having trouble scrolling around here. I can use these buttons, I guess. Okay, so let's see if we see the actual error, and we're not seeing it here. Auto result multiply error generated. So we're going to get an error if we try to instantiate our template with the types that we are passing in here, which are std string. CPP Insights isn't really helpful here, but hopefully you understand the problem. The problem is if the compiler tries to generate a template instance using std string, multiplying two strings isn't going to make sense. So the compiler is
that
going to
doesn't.
give you a compiler error
It don't
because
work.
this is not supported. So the message here is that you should make sure that the template instances generated by the compilers support whatever operations you are doing in the body of your function template. This is the message here. Another thing I want you to see before we close this off, I'm going to take out this problematic line here and we're going to go back to our maximum function. What I want you to see is that if you pass different types for this function template,
Wait,
you're going to get a compiler error.
Did he just delete the entire multiply one? Okay. Yeah. I guess we can go back to what was maximum.
And what do I mean by that? Let's take out our std string because it's no longer useful for our purposes here. And we're going to just use double and int parameters. Let's use int here and we make this an int literal. And then we call our maximum function. You see that we have a squiggly line because the function template is forced to use the same type for the return type, the first parameter, and the second parameter here because the placeholder is the same. So the compiler is supposed to use the same thing for the first argument here, the second argument, and the return type that we get from this maximum function here. But the problem is we are passing in parameters of different types. And this is going to give us a compiler error because the compiler wants to know what to do with the types that you pass in as arguments. And if we look at our problems tab here, Visual Studio Code should give us an error, no match for operator. This is the error we had before. We can try and build again. We're going to get a compiler error again, but this time it's going to be different. It's going to say no instance of
argument types are double and
maximum matches the argument list that we
well,
are
this
using,
directly
which
answers
is double and int. So
the question that I was asking at the beginning.
We will see ways around this as we progress in the chapter.
Okay.
But what you should
know
ways
around this
is that if we set up a function template like this, this is going to enforce for all the types where we will place in t to be the same. If they're not the same, the compiler won't know how to do its replacement, and it is going to give you a compiler error. Okay, the last thing I want you to see is that we can use the debugger to debug function templates.
Okay, so the debugger we were never shown how to install the debugger, how to use that. So hopefully he shows us how to do that. I was violated. My friend asked what I looked like, and I got called I looked like a trustworthy friend, one that wouldn't steer you wrong, one that totally won't kick you. And apparently I look like a friendly guy named Patches. Violated. Yeah, that's pretty violating to be called Patches.
So let's turn this back to int because we wanted this to compile. So let's take out the decimal point here so that we have proper int literals. And if we compile again, this should compile. Okay, the build is good. Now, what really happens if you try to debug a program with function templates? Are you going to be working on the template instances? Because remember, the function templates are going to generate function template instances with actual types. For example, our template instance here is going to have int because we are passing int as argument here. So how are we exactly going to debug this? Let's try this. We're going to set up a breakpoint here on the call to our maximum function, and we're going to start debugging. We're going to go to our run tab here, and we're going to use the debugging tools that come with GCC. We have seen how to do that in the last chapter, and we're going to start...
the fuck we did. No, we didn't. Oh no. Am I gonna have to find a whole second, like a whole other video that explains how to do that? Oh shit. I was really hoping that you would show me how to do that, Mr. Gakwaya. That would have been very helpful. Wait, let me double check, make sure I don't. Do I have that? Check DMs. Accurate. You do not vibe with this universe. Oh no. Oh no. Yeah. This is gonna be a side quest by the looks of it. We got a tasks.json. Oh boy. I believe clicking run and debug just sets up the debugger for you. I guess. Oh no. G++ active build file, detected task, compiler. I don't know which of these I'm supposed to press. I don't know if it matters. I guess I go with the G++ one. Oh. Holy shit. What the hell? Oh boy. Here's hoping that that was correct.
Debugging. Let's minimize this guy here so that we have some breathing room. And we're going to run our debugger. Let's maximize this a little bit and push this a little to the left. And we're going to start debugging and see what really happens here. So we hit the green button here. We're going to start debugging. Our code is building now. The build is done. The binary has been passed to the debugger, and now we have hit our breakpoint here. So let's minimize this a little bit so that we have an easier way to see this. We have hit our breakpoint. You see the locals are what we have in the main function, which happens to be to the top of the call stack here. Okay, now we want to jump into the maximum function.
I don't. Okay, so we have the call stack here. We got locals. His result is 0. Mine is 6,000 or 62,574. I don't know if that's I don't know. Oh boy. We got this. And this whole thing is just. This is the debug console. Thread 1 hit breakpoint 2 main. It has a file name, auto result, execute debugger commands. It looks kind of similar. It looks like it might be working. I don't know.
And see the types that we have inside. So what we want to do here is hit the step into function, and you notice it is going to jump into our function template here, but the locals here are not giving us the types, and this is because this is a function template. It's not going to give you the types because it's not easy to get those here. But if we look at the call stack, you see
it hasn't been assigned a value yet. It's fine. Okay. It's a garbage value. Garbage value can be anything based on compiler. Okay. Okay, that's good because I'm like looking at this like I don't know if this is correct or not because I wasn't told to set this up.
see that we have information about the types of the function that is being called. We are calling int a and int b, and it is going to return int. You see that in the angle brackets here. And again, this is possibly another way to look at what template instances were generated by the compiler. Because we see the function called here is taking int parameters, and it is going to return int. Let's kill our debugger because this is really all we want to see.
That's all you wanted to show me?
To double here. And we're going to see that the function to the top of the call stack is going to be taking double parameters. So let's change this back to 5 point something, 5.5 maybe, 7 and 0.9, why not? And we're going to print our result here. But what we really are interested in is seeing the function template instance generated by the compiler because of this call here. And we can do this through the debugger. This is a little bit convoluted because you have to set up breakpoints and whatever, but it is helpful if you don't want to use things like CPP insights, as we have seen before. And again, this is also useful because you will need to debug your code if it is using function templates. Let's run this to really prove our point here.
Oh boy. I guess we just hit the run and debug button. I like that X is 5.5, but Y is 7.9004 repeating. Until, wait, no, it's 0.000000004. Why? What? That's so weird.
The build is going to go through, the binary executable is going to be passed into
Wait,
the
it's like that on his too. What the fuck? I just noticed that's fucking weird. Why is that? That's a floating point error? Okay.
debugger, and we're going to hit our breakpoint here. Again, you see our locals are not giving us the types here, but we can use the function call stack to really see this. We have hit the breakpoint here at line 15, so we can step into the call. And if we hit the body of the maximum function here and look at the call stack, we're going to see that the parameters we have in our function call are of double type. And again, this hopefully proves to us that the compiler has actually generated a double function template instance. Okay, since we are debugging, we can actually try and follow this program. Let's hit next so that we can hit the end of this function. We can finish it and hit the main function. By the moment we hit the main function, result is going to be 7.9, which is what we have here, and it is what we're going to print. We can just step over this because we don't want to step into the logics of stdc out. So step over, we're going to print our result, and our debugging session is going to basically end because we have hit the end of the main function. Let's try and use the compiler from Microsoft to see the information it gives us, because these things can be different depending on the compiler and the debugging tools that you are using.
It's not your mistake. The big gods that made IEEE standard for floating point numbers have to deal with this too. Really? Oh, okay. So it's not my fault. It's not my fault. It's not my fault.
We have the luxury to have these two set up here. So all we have to do is switch the tool we want to use here.
Oh boy. So if I do this, Clang, G++. So I don't have one for Microsoft by the looks of it. No, wait, no, cl.exe. I think that's the one, right? Because I think CL is... No, that's Clang. Clang cl.exe. Clang plus plus. CLAN. G++. Maybe it is. I don't know. I don't have the one that's... I don't have any of them labeled MSVC. Alright. Oh, wait, no. Well... I don't know. I'm just going to watch the video.
And this is going to be using the one from Microsoft. If you are not on Windows or you don't want to use the compiler from Microsoft and its debugging tools, you can just use GCC and its debugging tools. Here, I just want you to see different ways to do the same things, and that compilers and debuggers can give us different information. We're going to try and debug with this, so we're going to hit the green button here. Notice that this is going to be using the compiler from Microsoft. If we look at the build output here, you see that we are calling cl.exe. It is what we are using to build our binary. The binary is going to be passed to the debugger, and then we're going to hit the breakpoint here as we know. And then we're going to have our output here. These are our locals. You see in the main function, we don't see the types of our locals. Why is that? I don't know why, but we see the values here in the main function. And if we hit the step into button to jump into our maximum function, A is going to have this value, B is going to have this value, and we look at the template instance, we can see the same information, but we are using a different compiler. This is really how you can debug your code that uses function templates, and this is going to give us a peek into the actual template instance that was generated by our compiler. This is really all I had to share in this lecture. And before I let you go, let's summarize a little bit.
Oh boy.
Function templates are blueprints. We have seen that the compiler is going to use those to generate actual function template instances. Real function definitions and declarations are going to be created when you call the function with arguments. If the template parameters are of the same type, maybe t and t, then the arguments you call the function with must also match, otherwise you'll get a compiler error. We have seen this.
Yeah, we saw that.
Here we have a point we haven't already covered. Template instances won't always do what you want. A good example is when you call our maximum function with pointers. So let's go back and really see this, because I want this to cover as much
Calling
as
a
possible
maximum
about
function with pointer.
templates, px, and we're going to initialize this with the address of x. Nothing sophisticated the compiler knows to do. We're going to take the types that we pass in here, which happen to store these guys in memory. Hopefully you can see that. And let's try and debug this. Progress contains an address and py contains an address. Hopefully, let's kill this because we have seen this information to the value inside this pointer. Let's build again. We can clear and run rooster.
Oh no! I died! What happened? I'm dying! I have no frames! ISP Chama, please. Please. Please come back. Please. Please let me stream. Let me stream, please. We were doing so well. Yeah, I'm dropping completely. Yeah, I'm like disconnecting and reconnecting. Oh, wow, I've like completely disconnected like 4 times. I'm disconnecting and reconnecting like a lot. What the hell? Mad at somebody for missing a stream. Wow, we are like completely screwed at the moment.